Hello everyone, I'm Gabriel Duflo, a research associate from the University of Deusto, and in this tutorial I will present to you how we use Explainable Artificial Intelligence for transparent and trustworthy road safety intelligence. So this is a map of Madrid with the location of different hotspots for vulnerable road users. So first, a vulnerable road user that I will call VRU in the future of this video because I struggle a lot pronouncing it properly, consists of pedestrian, bicycle, motorcycle, scooter, e-scooter, and so on. And a hotspot is a location with a higher risk of accident for those VRUs. And those locations are defined as a hotspot by counting the number of accidents that occurred for a past specific period. So depending on the type of hotspot, it can be 3 or 5 years, for instance. So now, having this in mind, this work has been driven by two research questions. First, can we predict the location of those hotspots but before the accident actually occurred? And once we have the location of a hotspot, can we explain what causes it? Okay, so the idea is like by knowing the cause, what we want is to help planning for intervention that can help decrease the risk of accident. So let's consider this intersection as an example, okay? And we want to use deep learning to predict the number of accidents for, let's say, 1 year. So the first thing is what information we want to use for that prediction. So what feature we want to use. So here we can consider a very simple model with 3 features: the number of traffic lights, the number of pedestrian crossings, and the speed limit. As I say, we want to predict the number of accidents, so we have to design a deep learning model which takes as input the features and outputting the number of accidents. So let's see what we have here. So we have an intersection with 5 branches, each of them having 1 traffic light, so 5 in total, same for pedestrian crossing, and the speed limit is 30 km/h. In case we have different branches with different speed limit, we can just consider the maximum one, okay? Just for this simple example. So now with this, we can encode the information at this intersection. So the encoding is very basically the fact to transform an information into a vector. And we want to work with vectors because they are mathematical objects that are very easily transformable by matrix computation, and so that we can use as input of a neural network. So for example, here at the top right, you can see a neural network with 0 layer right now. So we just see 3 neurons carrying the 3 input features. But now if we add a layer, this is the corresponding matrix computation. So each arrow actually carries a learnable weight that appears in the matrix below. And the last operation, alpha, is an activation function which consists of breaking the linearity of the operation, and generally this is a rectified linear unit. So this is the first transformation, but if we want to add another layer, we have another transformation. And finally, because we want a scalar value at the end, because we just want to predict the number of accidents, this is what the last layer looks like, okay? So by giving x as an input, we have p of x, so the prediction of x as an output. And now we have to learn the weight, so to choose the value for each of the weight, so that x, we have the good prediction at the end. So here, we consider 1 past year for the training the model, and during the chosen year, at this intersection, just 1 accident happened. So we have to modify the weight of the neural network so that given this 5530 as input, we get 1 as output. Okay, so now we have a model that is perfectly able to predict the number of accidents for 1 specific intersection. Now let's see what happened by applying this model on 2 other intersections. So the first one is an intersection that recorded 14 accidents and with the 0 traffic light, 6 pedestrian crossing, and 50 as a speed limit, 50 km/h. And the second one recording 4 accidents with 2 traffic lights, 3 pedestrian crossing, and speed limit of 50 km per hour. So now we give these encodings as input to our neural network, and here the prediction that we obtain. So 3 for the one with 14 accidents, and for the intersection with 4 accidents, we have minus 45. I think we all agree that this model is not very efficient in that case. And there is actually a way to measure this efficiency or inefficiency. This is the loss function. And a very classical way to measure it is to use a mean squared error, the error being the difference between the prediction and the label. So here, giving the values that we have for these 3 intersections, this is the loss that we have, like 840, it's more than 840. So if this a high loss, a low loss value, it's hard to say. But what we want is to minimize this loss, so to modify the weight of the neural network so that the loss is minimal. Ideally, it's 0, but usually it's not reachable. So now we learn the model, and these are the new values that we obtain. And here we see that the model is better because the loss is much lower. Now we have a loss of 2. Even though you will notice that for the first intersection, the model is worse than the initial one. But globally, we see that it's a better model given the lower loss. Now let's see what are the limitations of such a model of prediction. So here, let's consider this intersection, and we have the encoding information. So we know that on this intersection, there are 0 traffic light, 2 pedestrian crossing, and the maximal speed limit is 50 km per hour. So this is a possible situation for this intersection. But also this one, because we know that if we have different branches with different speed limit, we just consider the maximum one. Also this one is possible, this one, and this one. So we see that here the problem is like such an encoding information is not capable of depicting the exact topology of the intersection. Another scenario that may happen is, okay, let's consider that down one street we have another intersection with a traffic light, and for some reason the presence of this traffic light creates a traffic jam that propagates up to the first intersection. So in that case, the risk of accident of the first intersection is induced by the presence of traffic light of the second intersection. So this is another problem of this type of model of prediction, is like the input, the features only consider the local information of the corresponding intersection, but it doesn't consider the relationship between 2 close intersections. And one way to alleviate this issue, or to tackle this issue, is to consider the road network as a graph. So if we take a shorter area, to transform this road network as a graph, we will consider first the intersection as nodes, and the street linking 2 intersections as the edges. Okay, so like that, we can to create relationship between 2 close intersections. And now we need to assign features to each edge in each node of the graph. So for that, here is the features that we chose for the work I'm presenting to you. So you see that, for example, for the edge, there are much more features than the 3 that I presented before. So the only difference is the embedded information will be a larger vector. But in addition to this static features, we will assign other features, dynamic features, trying to depict the behavior of the drivers. So for that, first one is connected vehicle data that will record the harsh event of the vehicles, like turning left, turning right, brake, and accelerate. So depending on the location of this event, it will be assigned to either the node or the edge. And we will have travel demand data. So for this feature, it corresponds to an estimation of the number of vehicles going through the edge. Now that we generated our graph, we can just abstract from the road network itself and just work with the graph that we name as a couple n and e, n being the space of node and e the space of edges. And then we can use this graph as an input to a graph neural network. A graph neural network is a neural network not taking a vector as input, but a graph. So then we can use this graph. And how it works with the idea of message passing. Okay, so with this very complicated formula, the idea is like at each layer of message passing, each node will share its information to its neighbor, or will gather the neighbor's information. For example, let's consider this node in yellow. Okay, so when we will apply the message passing layer, it will gather information from its neighbor. So we take the first neighbor, and so we have encoded information from the node and from the edge. This can be used as input to some neural network, okay, that we can briefly define. So this in the formula is correspond to the function f_nai, and as it will return a vector, another vector as an output that will represent this neighbor. So we can do the same for all of the neighbors, so for this one and also for this one. Then, so we have some encoded information for all of the neighbors. We can add also the encoding information of the node itself, and then we will gather all of this information. So usually we can process a mean or a sum for all of the neighbors, and then we will aggregate it to the current node encoding to create a new encoding, which will be like at the level i+1 in the formula. Now, specifically to the context of a raw network or accident prediction, what does it mean? So here we have an intersection in blue from which we need the prediction of the number of accidents. Okay, so if we don't use any layer of message passing, the only information we have access to is the information of the node, which will be relevant, but maybe it will not be useful. So we want to add a layer. It will not be enough. So we will add a layer of message passing, and after one layer, these are the nodes that are used to compute all of the information that we need to compute the prediction is within this subgraph. Okay, so then we can expand it by adding new layers. For example, here with 3 layers. So what does it mean? It means that to compute the prediction of the node in blue, in this intersection, we will gather some information of some nodes for some intersections that are quite far. If you see like the red dot right at the top of the picture, well, maybe it's not the most relevant information to use for the prediction at the intersection in blue. So instead, what we want here in this work is to draw an area around the node that we want to predict the number of accidents. And all of the intersection within that area will define the subgraph to use for the prediction. And in our approach, for any layer that you add, the whole information that will be used will be within that subgraph. So let's see here an example with a very simple graph. So the whole process is called a node regression. Regression, in comparison with classification, it's because the values that we predict, so here's the number of accidents, doesn't take its value in a specific set of values. Okay, so here the number of accidents can be any integer without any limits. That's why it's a regression. And node regression, node because the prediction occurred at every node at the same time. So it means that at the output of this graph neural network, all of the nodes will have a prediction. If you get into it, and we want, for example, the prediction at this node, the first step will be to extract the neighborhood, as we saw with the area around this node. And once we extracted it, we will process this time a graph regression. So now the prediction will happen on the whole subgraph itself. So we can get into it again. And so at first we have the features for each node and edge. As I mentioned before, the first step will be to encode the information into a fixed size vector. that we can combine with the message passing layers. And finally, once all of the node has an embedded information after it passed through, I don't know, L layers, we will gather all of this information to one single node, to one single scalar value, which will be the prediction. So we experimented this model on the road network in Madrid, and these are the results that we obtained. And when you see that, you may notice that the difference that there is between considering all intersection and only hotspot. So you may be wondering why such a difference. So the thing is, one of the biggest challenges within these experiments has been the high imbalance in the data. You can see on the bottom left on the green curve that most of the intersection, and actually the extreme majority of the intersection, record 0, 1, or 2 intersection. So this forces the model to at least tend to underestimate the whole prediction, and it makes it very hard to predict a high number of accidents for intersections which actually have a high number of accidents. Also, we see that with the higher number of accidents, the prediction increases with the actual number of accidents. So, which is a good behavior, even though it's not, it still tends to underestimate the prediction. We see that considering a margin of 2 accidents for the prediction and the difference between the prediction and the label, delta here on the slide, we can predict 80% of a hotspot properly, and 98% considering % of all intersections. So of course this could be improved, but now let's take a look on what happens in a map. So here you see a map where all intersections are represented by 2 colors. The inside corresponds to the label, so the actual number of accidents, and the color on the border is the prediction. And I want you to take a look at this in this area. So gathering 8 close intersections, and for these 8 intersections, you see that the prediction is not so close to the label. So like that, if you take the global error, you will just sum up the error for each intersection, which will lead to a big error. But if you consider this 8 intersection as one big intersection, because actually these 8 intersections are within the same area, you see that the total number of accidents is 38. If you sum all of the prediction for this 8 intersection, you reach 35. So the error is actually not very high. So this shows what generally happens with this model, is that there is a room for improvement if you consider the prediction at the level of intersection. But if you increase a little bit the granularity and you consider together intersection within the same closed area, then the model is perfectly able to detect area with a higher risk of accident, which was the initial purpose of this work, to detect hotspots. So everything that I have presented so far corresponds to the first module of this work, the deep learning prediction module. So for predicting the number of accidents at street intersection. But those predictions are what we call black box. So you don't understand how the model transforms the input feature into the output number of accidents. So that's why we want to incorporate a new module, an Explainable AI module, whose purpose is to interpret these predictions. And the idea is that we emphasize the features that are more impactful for a specific prediction, and this will help to understand what causes this potential high number of accidents, and also help planning for intervention for reducing that number of accidents. But this I will present to you an example now, and you see on the figure you see that this model of explainable AI is divided into two parts, a GNN explainer first and then GraphLine, that I will explain right now. So for GNN explainer first, so let's say that we want to explain the prediction made at this location. So like we saw before, this is a subgraph that the prediction module use for the prediction. So we will use also the same subgraph for the explainer. And so to this subgraph, we will add features like the position of the traffic lights, the position of the pedestrian crossing, and the parking spot on the side of the street. And to make it simple, we'll stick to these three features. And with this single prediction, we will generate a dataset by adding a random noise to these features. And for example, here we generated 5 data points, so with 5 fake prediction. And we will try to remove features to see how the prediction evolves. For example, here we remove the traffic light features, and so we see the evolution for the prediction. So ideally, you want like each bar reach the star, meaning that the prediction is the same as the original prediction. So we try with other features. For example, now we remove the pedestrian crossings. Now we remove the parking spot, but here we remove one by one. Of course, when you search which features to remove, you will try to combine. So for example, here you remove 2 features at the same time, and so you try with all of the possible combination. This searching process also happens for the edge. So we'll try to remove edges to see which one has an impact on the prediction. So for example, we can remove this area or this area, but it doesn't have to be the same area. We can remove edge from anywhere, like that, for example. And we will try to combine this edge removal, the mask for the edge, with the mask for the feature. For example, here we combine both, and let's say that this is the combination that leads to the best explained prediction. So the prediction that is as close as possible to the original prediction. Now this is given as an input to the second step of the explainer, which is GraphLine. And GraphLine will just use all of the features that have been selected, so from the selected edges, and try to evaluate their impact on the feature. So the idea is to assign a weight to each feature independently, and so that the sum is close to the original prediction. So for example, we can imagine something like that we value more some features. So the color indicates if basically it means the color indicates whether the weight is negative or positive by a different organization. And this one, for example, is the one leading to the best explained prediction. So with where you see on the right, the bar are very close to the star. So the explained prediction is very close to the original prediction. So this is the type of result that we obtain for one specific intersection in Madrid. So here you see the output of GNN explainer. So on the right side, you see the features that have been selected. So the feature that are kept and say that they have an impact on the prediction. And on the left, you see the red edges are the edges that are considered to have an impact on the red dot prediction. And above that, we can add the output of GraphLine. Instead of showing the impact of all of the feature, which will not be readable on the figure, I will keep just the 5 top impactful feature for this specific case. And you see that, for example, the car parking on the right side in the indicated location is negative, has a negative impact on the intersection, meaning that if we remove the parking, it will increase the safety. On the opposite, the traffic light and the cycle park on the indicated location tend to increase the safety, so to reduce the number of accidents. So this, for example, could be represented by intervention that we can plan, like for example, remove the car park on the right side, or to, if there is no traffic light or cycle park in the indicated location, we can plan to install a new traffic light. So all of this is validated by a decision maker, a human decision maker that can say, okay, maybe we can do that or not. Like we see also the two other features that have a positive impact from the model. So we have the surface type, which is unknown in that case. So I think this one just means that because it's unknown, usually it corresponds to asphalt, so which is a normal surface type. So this is not so meaningful, I would say. Also, another thing which may be counterintuitive is the speed up count, which has a positive impact on the safety, meaning that the more harsh event corresponding to the speed up, the less accidents. This could be explained by the fact that this intersection is a big roundabout with traffic lights, and the more speed up correspond to the less cars, and so the lower chance to have an accident. But so this is not so clear, so that's why they still need to have a human decision maker behind this. But this still helps the decision maker to plan for the intervention. Also, just to explain what is the number of accident prediction explained and unexplained. So the number of accidents is, during the years that has been chosen for training the model, there were 8 accidents. The prediction unexplained is the output of the prediction model, the deep learning prediction module. So the prediction that we have is the original prediction, and the prediction explained is the number of accidents that we plan with the linear regression that we have from GNN-explainer graph line. So meaning that it's not so far from the original prediction. As a short-term continuation for this model, what we want is to automate the visualization of the Explainable AI module. So far, the output of GNN-explainer is still automated, but the one of GraphLine, selecting the feature, taking the image to visualize the situation, all of this is not automated yet. We still need to manually take the picture from the output of GNN GraphLine. So this is as a short-term continuation. Also, we can use this methodology to extend the model. For example, we can limit the deep learning prediction module to accident with only material or physical damage, for example. So we can filter which type of accident we want to predict. Also, we can convert this deep learning prediction module into a hotspot prediction directly instead of having the number of accidents. And also, this methodology is totally transferable to any city. Maybe the methodology is transferable. Maybe you will need to retrain the model, but we hope that with a trained model, you can use transferable learning, so that if you use it to another city, you can just train from the trained model, to use the trained model as a base for the new model. And this has been presented to the European Transport Conference in 2025. This is my contact, and also all of the partners that have helped during this for this work of SOTERIA. And I thank you for listening to me, and I hope you enjoyed this video, and bye.